This is lesson 2.1 on inductive reasoning. So there's two kinds of reasoning that we use in math. One of them is inductive, which is what we're talking about in this lesson. The other one is deductive. Deductive is what you typically think of in math, solving math problems, going step by step, applying rules, applying procedures, maybe solving an equation, add 2 on both sides. That's a rule that you're allowed to follow. That's called deductive reasoning. The reasoning that we're going to talk about is called inductive. Okay, inductive is the process of using observations to make conjectures. Conjectures are what we think of as educated guesses in math. In science, what do you call an educated guess? Well, the word hypothesis is used for educated guess in science. We have a different meaning for the word hypothesis, so we use the word conjecture or conjectures. So we try to make true conjectures, but sometimes conjectures are false. So you look at a pattern, you try to make an observation, you try to make this conjecture, and then you sort of see whether or not it makes sense. Okay, so the next figure in the pattern. We've got circles divided into quadrants by perpendicular diameters, and the little dot is moving around the circle. So looks like our next picture, and I'm drawing this freehand, it's really kind of terrible. So our next picture would be a circle of the same size with perpendicular diameters, and our little dot would be in the lower left corner. Okay, the next ones are patterns. Again, we're looking for patterns and trying to make an observation to create a conjecture. It looks like each time we are subtracting 2. Which means that our next term would be -3. For the next pattern here, it's kind of helpful if you ignore the negative signs for a minute. What do you notice about 1, 4, 9, 16? Well, hopefully you see those as being perfect squares. Well, what does that mean? Perfect squares are numbers that you obtain by squaring a counting number. So 1 squared is 1, 2 squared is 4, 3 squared is 16, 3 squared is 9, 4 squared is 16. So on this one, we have perfect squares, and we have alternating signs, and we're going from positive to negative and positive to negative. So we're going positive, negative, etc. So our next number here would be 25, and it would be positive since we're coming from a -16. All right, and then the last one, this pattern can be described a couple of different ways. You may think of it as multiplying by something. What are you multiplying by to get from 1/2 to 1/4 and from 1/4 to 1/8? Well, you're either multiplying by multiplying by 1/2, or you can think of it as dividing by 2, which with fractions, most people probably find multiplying by 1/2 to be easier to think about than dividing a fraction by 2, but it's the same thing. And therefore our next number would be 1/16 in that pattern. Another way of thinking about this is kind of interesting. What do you notice about these denominators? So you have 1/2, 1/4, 1/8, 1/16. The next one would be 1/32. What do you notice about these numbers down here? Well, hopefully you see that's 2 to the first, and that's 2 to the second, and that's 2 to the third. They're powers of 2. So another way to describe this is that the terms are 1/2 to a power, where n is the number of term it is. So for the first term, it's 1/2 to the first. The second term, it's 1/2 to the second. So that's kind of a more interesting way of describing it. It's probably not easier, it's just more interesting to think about. All right, and then in this next pattern, we have 3 pictures here, We're trying to figure out how many squares would be in the next object. There's kind of two sort of common ways to think about this picture. So first of all, how many squares are in the objects that are there? Well, we have 1 in the first one, and we have 4 in the next one, and we have 9 in the one after that. So the next one seems like it should be 16. Why is that? Well, notice that these are also perfect squares. So it seems like we should end up with 16 in our next little object here. So one way to think about it is to say, I'm going to take that little square there, and I'm going to build around it. So in my next phase, I've got, here, let me use the highlighter instead of the pen. And then, so we've got our little square there. In our next phase, we're going to build around it. So we're going to copy that little square over and then put little squares all around it on the sides and top. So then if we do the same thing in our next step here, so now we're going to take the previous little diagram here that we have, and we're going to build it. You can kind of see it here by putting the little squares around the sides and on top. So that means in our next one, if we take this whole little guy here and copy it over, and then build around it. So here we have, oops. So here we have our little square, and then our 3 little squares, and then our 5 little squares in the bottom. And if we add the little squares around it, we'd have one on either side here, and we'd add one there, we'd add one here, and we'd add one at the top. And there's our 16. Another interesting way of building that next figure is to take the shape that we had before and kind of slide it up and slip another row underneath it. So if we had this guy before, we're going to slide it up, it would be here, and slide another row underneath it that's 2 units wider than the previous one. So if we take in this shape, take that and slide it up, we would be putting this next row underneath it. So in any case, we would get 16 in the next object, and it would be perfect squares, and the objects would look the same. It's just sort of 2 different ways of getting there. I want to go back to something. I just remembered that I forgot to kind of mention this back here. Notice that getting from 1 to 4, you add 3. Getting from 4 to 9, you add 5. Getting from 9 to 16, you add 7. Notice that the primes are spread out by consecutive odd numbers. So the difference between consecutive squares is going to be an odd value. That pattern is kind of interesting in primes, and you may not have kind of seen that before. All right, so again, to recap, inductive reasoning means look for a pattern and then make a conjecture, which is an unproven statement based on your observations. And then you try to test up the conjecture to see if it's true all the time. So does what you think the pattern is, does that work for every stage going forward? So here's an example of making a conjecture. The sum of 2 odd numbers. So 1 and 3 are odd, their sum is 4. 1 and 5 are odd, their sum is 6. 3 and 5 adds to 8. And the odd numbers 7 and 9 add to 16. What do you notice about all of these numbers? Well, they're all even. Why does it make sense that the sum of 2 odd numbers isn't even? Now, you kind of want to think about why that's true. Are we actually going to give a proof? No, but we're going to sort of talk about why that makes sense. Well, remember that in algebra, when you want to represent an even number, you would represent it as 2 times a number, 2n or 2x. So that means that an odd is represented as either 2n plus 1 or 2n minus 1. So suppose you add 2 odd numbers together. So let's say the first number is 2n plus 1, and the second number is 2m plus 1. So you have 2 different odd numbers. Well, why will that be even? Well, notice that this little one sitting here on the outside, these parts are even, right? Those little ones, what happens to them? Oh, they group up. Now they're equal to 2. So when you add those terms together, you would get 2n plus 2m plus 2, which is an even number because that is divisible by 2. So basically just think about how, if you had 3 things, 2 of them group up and you have 1 left over. That's the way every odd number is. You can pair up all the numbers and then there's 1 left over. Well, if you have 2 of those odd numbers, you've got a leftover here also, right? Now, what can you do? You can take this one and put them together, and they pair up, and now everybody has a partner. All right, so for this conjecture here, we're kind of trying to figure out the sum of the first n odd positive integers is. We're going to make a little table here. So let's say that our first column is n, and then we're going to add the numbers, and at the end we're going to try to figure out a formula for the sum. Okay, so the first one odd positive integer is 1. The sum is 1. The first 2 odd positive integers would be 1, and what's the next odd positive integer? Well, it's 3. What's that sum? 4. The first 3 odd positive integers, 1 plus 3 plus, what's the next odd positive? 5. That adds to 9. The first 4 odd positives, 1, 3, 5, 7. Do you see the pattern? What do you notice? What's special about these numbers over here? Well, kind of like we said before, we're getting perfect squares here. So that means I want you to tell me if I put n number of terms here, if I added 1, 3, 5, 7, however many I need to get n terms, what would it add to? Well, look, 1 to 1, 2 becomes 4, 3 becomes 9, 4 becomes 16. N gives you a sum of n squared. The sum of the first n odd positive integers is n squared. All right, and then another term here, a counterexample is an example that disproves a conjecture. If you want to prove a conjecture is true, you have to give kind of like a long argument. To prove something is false, all you need is one example that shows it's not true. So remember when we talked about always, sometimes, never? Always statements are statements that are true, always without any exception. False statements are either never true or sometimes true. If there's even one counterexample, a statement is false. The question is whether is it sometimes false or is it completely always false. But it's kind of easy to prove a conjecture false versus true because false just requires one example to disprove it. So show the conjecture is false by finding a counterexample. Notice that they're telling you the conjecture is false. You don't have to sit there and try to decide if it's false. It says show it's false. All odd numbers are prime. Well, some odd numbers are prime. So like 11, it's odd and it's prime because the only factors are 1 and 11. But not all odd numbers are prime. What's an example of an odd number that's not prime? So an odd number that has factors other than 1 in itself. Well, for example, 9. 9 is odd, but it's not prime. Because it's divisible not just by 1 and 9, it's also divisible by 3. Other examples, 21. 15, 27, 45. Okay, now why would a number like 19 not work? Well, 19's odd, but it's also prime. So it's an example of when this is sometimes true. It's not a counterexample. Why would the number 2 not work? Well, 2 is prime, but it's not odd. So in order to be in a counterexample, it has to be an odd number that's not prime. And then lastly, a counterexample to this statement. Well, let's suppose, I'm just going to pick two numbers. Let's use A as 1 and B as 2. And let's see if this works. Well, in other words, doesn't work. So if I pick two numbers and when I plug them in, it makes the statement true, that doesn't mean it's true all the time. It just means that I found a value for which it's true. Maybe it's true all the time, maybe it's not. But since I'm trying to disprove it, that means I want to come up with numbers that when I plug them in, it will not make the statement true. So 1 plus 2 on the left side is being squared would be 3 squared, which is 9. On the right side, they're doing 1 squared plus 2 squared. Well, that's 1 plus 4, which is 5. Those are clearly not equal. That means that we have come up with a counterexample. Now, another reason that you would know that that's false is because remember, when you multiply a plus b squared, when you multiply that out, how do you square that? You don't just do a squared and b squared. That's not how you simplify that. What do? You do, get rid of this. You do squaring means multiply by itself. How do you multiply a plus b by a plus b? Well, what's this called? A times a is a squared. ab and ab is 2ab. And b times b is b squared. Some of you might have learned that as foiling. So if you didn't FOIL correctly, you would be missing that middle term, which is what's happening there. So they've given you kind of a common algebra mistake and said that a plus b, the quantity squared, is the same as the square of the individual numbers, which is added together, and that's not true. So again, in this problem, it said show the conjecture is false. So make sure you read, because sometimes they give you information in the problem in the directions that are helpful to use. This is the end of lesson 2-1.